This is lecture 10. So up until now we have been discussing about S parameters from the perspective of incident voltage and reflected voltage and so on and so forth. In today's class we would uh, uh, like to take one more step, and we would like to talk about it from the perspective of power. Okay, so I mean it's basically an extension of whatever we have been doing. So again, let's say I have a input source, and for all RF applications we assume that the input source is associated with the resistance R because that's the practical scenario. And let's say we have a long transmission line and there is some termination disconnected here, and in general I have a forward going voltage wave, I have a reflected wave and so on, and I have a forward going current wave. The current wave is V plus by Z naught, reflected wave is V minus by Z naught, right? So at a so now if I can express voltages and currents in terms of waves going having certain direction, then I should be able to it should naturally follow that I should be able to express power uh, uh, associated with the waveform going in a certain direction, right? And what is power? Power is nothing but average of current times voltages, right? Uh, so, so if I simply, I mean, at a very rudimentary level, if we assume that is V plus and the V plus is real, right? Uh, I can simply say that, or you don't even have to assume that V plus is real. I can simply say that the incident wave or incident power is equal to incident voltage times the incident current, an average of that, right? So which is nothing but mod of V plus squared by Z naught, where obviously I have assumed that V plus is the RMS voltage, right? Where my assumption is that V plus is equal to RMS value of the incident wave, incident voltage wave. Similarly, the power reflected, right? So I will refer to this P incident as Pi, and I will refer to P reflected as PR. Is nothing but, I mean, using the same analogy, is V minus squared by Z naught. So what is the total power that has gone into my my network? Now note that the network definition starts at this edge, right? So what is the total power that has gone into the network? So P total, that is into the network, is nothing but mod of P plus squared by Z naught minus mod of P minus squared by Z naught, which I can also write as V plus squared by Z naught 1 minus mod of V minus squared by V plus squared, right? So if I rewrite it, what do I get from the definitions that I know? So the power delivered, okay, so which means that what is V plus squared? This is nothing but Vi squared by 4. And what does V plus mean? V plus essentially means, what does this mean? This, so V plus effectively means This is the voltage at the junction. This is identical to, I should not say equal to. So definition, P plus is equal to the voltage at the junction the total voltage at the junction if the junction was perfectly reflectionless, i.e. matched. Okay. So if Z0 were equal to R and RL was also equal to R, then this junction would have been reflectionless. But it looks like V plus, by definition, by our definition of V plus, it looks like V plus is equal to that voltage which which this junction would have observed if the if there was no reflection at all, which means that Vi squared by 4 or V naught squared by Z naught, which is Vi squared by 4 Z naught, is equal to the power transferred into the network under reflectionless condition, right? I.e. reflection match condition. Okay. So now let's look into this equation that we came to. What is the power delivered, right? So what is the power delivered? Let's look into this. There's a more generic case. So the power delivered is nothing but, so the P delivered is nothing but power incident, or rather power under matched condition P in under matched condition times 1 minus gamma squared, right? And if I assume that your input resistance is real, right, so then reflection match and power match conditions are identical. So this is equal to the maximum power delivered that can be delivered to a load, right? This is the maximum power that can be delivered to a load minus the 1 minus the reflection coefficient square, right? So this is if R is, or if Z naught is real and source resistance is also real. I have assumed real in this, but in a more generic case. Okay. Okay. So why is this useful? This is useful because we always know what Pmax is, right? You know the source. If you know the source resistance, you know what is the Pmax is. And gamma can be easily measured, right? So you have, just like you can measure uh, impedances by impedance meters, you can have big boxes of which are generally called vector network analyzers or VNAs. You can measure the gamma fairly easily, which essentially means that uh, if I just get the value of gamma, right, I should be able to find out what is the net power that is going into a system, right, or the net power that I am extracting from from a load. Okay. So now this also has some interesting byproducts. I mean this analogy, and the byproduct is as follows: that we all know that the capacity. If let's say I have a network and I have a capacitive load here. Okay, and I ask you what will be P delivered. We all understand that P delivered should be 0, right? Because the capacitor should not be able to draw any power, and you will see that readily this will come out because of what? Because the reflection coefficient here, gamma L. So if I find out the reflection coefficient at this node, let me just make it simple and I get rid of the transmission line in totality. Let's say I have a capacitor here. So what is gamma here? Gamma is nothing but 1 by j omega c minus r by 1 plus 1 by j omega c plus r, which essentially means that mod of gamma is 1, which means that directly from the equation that you have, you see that the power delivered will be 0. So in a nutshell, if you have a completely imaginary load, it can be capacitor, it can be inductor, it can be anything, then you will see that mod of gamma is is always equal to 1, and hence the power delivered into the load is 0. And on the other hand, uh, on the other hand, if there is a if there I if I have to have a power delivered, it essentially means that gamma should have a real part, right? So there should be a essentially a resistive element associated if I want to have a if I want to have some power actually extracted from the source and delivered to the load. Okay, so that is as far as the reflection coefficients are concerned. And now let's turn our attention to something that you will see in many designs, and if you read research papers, you will often see sometimes um, the measure of a good match, whether the input is actually matched or not, right, is obviously been one way to measure that is through the reflection coefficient or S11, right? So, but if Z naught is if R is exactly equal to the impedance looking in, or the impedance looking in is exactly equal to R, then clearly your gamma is 0, right? But that need not necessarily always be the case, because it is almost anything else in life, you will never get the impedance to be exactly equal to whatever it is. So which means there will be some deviation, right? What I am trying to get at here is that gamma is essentially ZL minus Z naught by ZL plus Z naught. So if ZL is not equal to Z naught, we clearly know that there is not we do not have a match. But how do I know what is a good match? Right? Is ZL equal to Z naught plus 0.1 Z naught a good match? Or if ZL equal to Z naught plus 0.01 Z naught a good match? So people came up with some definitions of a good match, and the definition of the good match is again based on this. So P delivered is equal to P max 1 minus mod of S11 squared, right? So this corresponds to the reflected power, right? So good match means mod of S11 squared should be much less than 1, right? So typically if mod of S11 squared is less than 0.1, i.e. 90% of the power is delivered, of the max power is delivered it is considered to be a good match, right? It is considered to be a good match. Now note that this is quite heuristic, right? People had to come up to some value. You can choose 95%, you can choose 99%. People came up to 90%. So it is what it is, right? So if we stick to this definition, then essentially in terms of dB, right? So S11 in dB terms should be less than what? We just basically take 10 log, right? Should be less than minus 10 dB. Right? So that's why if you see any data sheets or if you read any papers, often the idea of a good match is your S11 should be less than minus 10 dB, right? Okay. The next thing that as designers we should be cognizant about is the relationship between S21 and the voltage gain. So note that I am talking about S11 and S21. The same thing can be uh, you can extend the same thing for S12 and S22 because that's basically you change the ports, right? So whatever we are doing for S11 and S21 is applicable for S22 and S12 also. Okay. So having said that, so let's say I have a matched transmission line, everything is good. This is R, this is R, this is VI, right? So what is S21? Everything is matched, there is no reflection anywhere. Note that your port is this, right? So this is your junction, because in RF almost always we assume that if particularly if you are doing receivers, it is assumed that the VI is associated with R. You are not able to remove that R from the VI, right? It comes with the source, right? And since we are always talking about matching, which means every interface should have some R associated with it, right? So the definition in RF is slightly different from analog. So we talk about the interfaces, not the original source. Okay. So what is V plus? So there is always V plus in this case because everything is matched. There is no reflection anywhere. So this is V plus. This is V plus e power minus j omega tau, right? Where tau is the length of the delay of the line, and there is no reflection, which means that your V naught is also equal to V plus e power minus j omega tau. So what is S21? S21 is essentially e to the power minus j omega tau, or mod of S21 is equal to 1. Okay, but what is V naught over Vi? So V naught is clearly V plus e power minus j omega tau, and what is V plus? This is Vi by 2 e power minus j omega tau, right? So what is V naught over Vi? Mod of that, this is equal to 1 by 2. Note that this is not the same as S21. Okay. Why? Why it is not the same as S21? This is not the same as S21 because typically if we are coming from analog background, we are used to defining gain from the source to the load, right? But again, we are essentially defining gain from port to the port, right? So S21 is essentially the gain from port to port, and if you are okay, if you are defining your gain from this V1 to output, then fine, then S21, then you can have some equivalence between S21 and V1. Okay, but this is again under matched condition. Now, if you recall, we had talked about this briefly in one of the in probably the last lecture, that you have to be careful about voltage gain and S parameters if your interfaces are not matched, because by definition S21 is equal to S21 is valid under matched condition. Only when all ports are matched. So the crux of the matter is you will have to be very careful in associating the voltage gain as we know it, because voltage gain, total voltage is the sum total of reflected wave and forward going wave, right? So unless ports are matched, the total voltage is not equal to the voltage traveling through the port, right? So when you find out S21 later on in your in your various profiles, let's say in your job or in simulation or in testing, then you should before jumping to the conclusion that S21 is essentially the voltage gain, you have to ensure that things are properly matched. I'll show you an example of why I am saying so. So let's say again I take a very simple circuit. This is R, and let's say I have a transmission line whose Z0 is equal to R1, and this is R1. Okay, and let's say this tau d tends to 0, right? So I do not want to carry over the e power minus j omega theta, right? So now what is happening? So now let's say I have this port plane. This is often called a reference plane in RF parlance. Let's say I have this plane or this junction. What is the incident wave? I have V plus. What is V plus? V plus is Vi by 2. We know that, right? Similarly, I have a V minus, and V minus is gamma V plus. Now what is gamma? For gamma, I need to know what is the impedance looking in. Now what is the impedance looking in? Now note that any waveform, if I isolate this part only, so this is R1, right? Z not equal to R1, and this is also R1. So essentially this contraption has a matched load, right? So whatever goes, so this is matched. So whatever voltage waveform goes this way does not return back, right? So this is a matched contraption. What is the input impedance looking in? So your Rin is essentially equal to R1, right? So what is V minus then? What is gamma then? Then essentially gamma is equal to R1 minus R by R1 plus R, which means your total voltage, that is V1 at this port. I'm calling this port V1, right? Total voltage V1 is V plus 1 plus gamma, which is Vi by 2 times 1 plus R1 minus R by R1 plus R, which is Vi times R1 by R1 plus R. Okay, fine. So this is, as far as V1 is concerned, this is the total voltage, right? So now I want to find out the output voltage. What is the output voltage? This is essentially the output voltage. So now note that because this guy is matched, right? Because this guy is matched, whatever voltage, whatever voltage waveform that flows in this way doesn't come back, right? So if I call this, should call this something, right? Let me call this V2 plus. This V2 plus will go and get absorbed here and nothing comes back. So what is just on the right side of the junction, what is the total waveform? That is V2 plus, right? So if I call this x equal to 0, so at x equal to 0 minus, V1 is equal to Vi times R1 by R1 plus R. So at x equal to 0 plus, right, your V1 is equal to, simply I called it V1 0 minus, this is V1 0 plus, this is equal to V2 plus, right? And because there is no discontinuity, right, so therefore V1 minus is V1 at 0 minus is equal to V1 at 0 plus. So therefore your V2 plus is equal to, also equal to V1 Vi R1 by R1 plus R. Therefore your final V naught is basically delayed version of this. If I just say mod of V naught would be Vi R1 by R1 plus R. Okay. So uh, so what is V naught over V1? So V naught over V1 is essentially the same thing, that is equal to 1. But what is S21? But what is S21? S21 is what? Forward amount of voltage that is dumped into the output under matched condition. Output is matched, right? Because you had a transmission line of certain, assume the transmission line is a part of the output, so that transmission line has the impedance of R1 is matched to R1, output is matched, right? So so S21 is essentially your V2 plus, or mod of S21 is essentially V2 plus by V plus, which is equal to, so V2 plus is Vi R1 by R1 plus R, and V plus is Vi by 2, which is nothing but twice R1 by R1 plus R, right? So this definitely is not equal to V naught over V1. And if R1 is clearly if R1 is equal to R, then yes. But if R1 is, let's say, more than R, then you might get a condition in which your S21 is higher than is your S21 is higher than whatever you were supposed to get, and you'll be feeling very happy. But moment you check the input match, you will see that the reason you are getting your S21 better S21 is because your input was unmatched, right? So the key takeaway is, so this is because input is unmatched. So key takeaway, check S21 along with S11 always. And another key takeaway is S21 is not equal to voltage gain, right? It is some special condition under which S21 is equates to voltage gain. Okay, let's stop here.